We present MV-SSM, a novel multi-view state space model for 3D human pose estimation. MV-SSM incorporates state space modeling into visual token reasoning, by explicitly modeling joint spatial sequences at both visual and geometric levels, allowing more accurate and generalizable keypoint estimation, even under occlusions or novel camera configurations. We aim to estimate the 3D pose of multiple persons present at a scene, which is captured through a multi-camera setup. For this task, two primary sets of approaches exist. This includes the multi-stage geometry-based approach, and the end-to-end learning-based approach. Multi-stage geometry-based pipelines involve detecting 2D keypoints, matching them across views, and triangulating 3D positions. However, they struggle in multi-human scenes due to error propagation. In contrast, recent end-to-end supervised learning models suffer poor generalizability, often overfitting to specific camera setups from training data, and failing in new settings. Relying on traditional cross-attention on extracted tokens would extensively interact with the features across all spatial locations from multiple views. However, this leads to high computation costs and inefficiency due to multi-view features being involved. Comparatively, the projective attention enhances efficiency by avoiding global token interaction, and instead leveraging localized deformable sampling around projection anchors. However, it lacks the capacity to capture high-order dependencies between joints. To address this, we introduced the Grid Token-Guided Bidirectional Scanning or GTBS, which is integral to the projective state space or the PSS block. GTBS modifies Mamba's unidirectional scan to bidirectional scanning. This enables the PSS block to effectively learn interjoint dependencies in 3D space, while progressively updating tokens through both appearance and geometric cues. A naive direct application of Mamba results in an inaccurate performance, since the original Mamba architecture is not tailored for joint-wise modeling across static multi-view data. The PSS block combines projective attention with visual state space modeling, encoding both spatial alignment across views and joint correlations within human poses. The MV-SSM model is simple. First, we feed the multi-view images through a ResNet 50 backbone to extract multi-scale visual features. Next, these joint representations are iteratively refined by stacked projective state space blocks. These blocks leverage projective attention and state space modeling to progressively refine the keypoints. The final 3D keypoints are estimated via geometric triangulation. Extensive experiments on multiple benchmarks demonstrate that MV-SSM significantly outperforms other state-of-the-art methods. MV-SSM achieves improvements of 10.8 points AP25 on CMU Panoptix 3 camera setting, and 15.3 points PCP on Campus A1, showing state-of-the-art generalization. We additionally present an ablation study to verify the effect of proposed components, both qualitatively and quantitatively. This confirms that omitting GTBS or Mamba blocks leads to notable accuracy degradation, validating the necessity of modeling spatial structure and bidirectional joint dependencies in the PSS block. Qualitative comparisons highlight MV-SSM's advantage in occluded or complex scenes. In scenarios where MV-Gformer struggles, for example in partially visible limbs or challenging postures, MV-SSM provides more anatomically plausible and accurate keypoints.